Hello everyone, May 29th. Alright, much earlier today. It's actually I finished work around 10:30, and then I went to train, and now I'm here doing this. So yeah, much better than yesterday. Alright, let's see what we have. Find closest node to given two nodes. We're given a directed graph, n nodes numbered 0 to n-1, where each node has at most one outgoing edge. Each node has at most one, so it either doesn't have an outgoing or one outgoing. Graph is represented with a given zero index array edges. Yes, because there's only one, we only need a 1D array of size n, indicating that there is a directed edge from node I to node edges I. If there is no outgoing, we minus 1 that position. You're also given two integers, node 1, node 2. Return the index of the node that can be reached from both node 1 and node 2, such that the maximum between the distance from node 1 to that node and from node 2 to that node is minimized. Let me read that again. So we want to return the index of the node that can be reached from both. Okay, so node 1 and node 2 both can reach that index, such that the maximum between the distance from node 1 to that node, so the maximum distance between node 1, let's call it node x. So the maximum from node 1 to x and the maximum from node 2 to x is minimized. So we basically need to find the max. So we want to find a node such that the maximum distance to reach it are minimized. If there are multiple answers, return the node with the smallest index. I think some example is definitely needed for this. So basically we want the maximum to be, let's say, the same, right? That would be ideal. Well, let me get some water. All right, so example 1. We have 1, 2, 0, and 3. All right. And so node 1, so this is node 1. Node 2 is node 2. So we want to find a node, right, such that, so like if I find 2, then the answer is 0, right? And 3, the answer is 0 as well. Oh wait, hold a second. The maximum between the distance and, oh, it's not the difference, it's just the max, the min max, right? So we get a max distance for this, the max distance for the other. All right, is the max distance always the direct path? Because you have at most one edge, right? You have one edge leaving it, which means it's not possible to reach a node via two different edges, or two different paths. So if we have one path, let's say we have another path, then at a certain point someone has to branch out, but you are not allowed to branch out because you have at most one outgoing edge, so you're not allowed to branch out. Therefore, it is just a direct path, right? So we can ignore the max part. We just say, given two nodes, want to find a node such that the path is minimized. Let's get another example. 1, okay, 0 point into 1 and 1 point into 2. And we have 0 and 2. So this is negative 1. No. How can you reach this from 0 to 2 is 2. And from 2 to 2 is 0. The maximum is 2. Oh, I see. Yeah, that is true. That is true. You have something you can reach. So min max and we want to find a distance. Okay, starting from one node, I can find the distance to every single other node. Starting from the other one, I can do exactly the same. We can find every single node at a certain position, right? And we can just go through them and see which one is the, exactly. This is exactly how it is. You have one node, and I can have an array with all the indices of the nodes, and we say starting from 0, right? Well, to itself is 0, to 1 is 1, to 2 is 2. That's it. That's 0. For 2, starting from 2, I can't go out, so everybody is negative 1 except for 2 itself. That's a 0, right? So now we're going to go through this, right? Go through this, and this is the 1 that's possible, so it's going to be 2. And we're just going to count the minimum of this. And in fact, we do max on this. Okay, I think we have a strategy. But we'll have to run this twice. Starting from different node, right? I wonder if we can do a better way. So we're starting from one of them. We traverse the whole thing as much as we can. And so we start from one node, and then we start traversing. And the other node is on the path. Right? If the other node is on the path, then any node further down, because we're taking the maximum, is going to be bigger. So if it's on the path, then the answer is just the current path. Right? The answer is just the current path. So as we traverse, this is something we can do. Well, the other one is we go this first. We didn't find anything, and then we get the answer, and then so I can actually cache it. Oh, it doesn't matter. Right? It doesn't matter. So they're either on the same path. So one way or another, I will be able to find it, or they are not on the same path. Right? If they're not on the same path, they might merge somewhere. And if they merge somewhere, right, we'll take the one with the longer path. right? We take one with a longer path, and we cannot keep going, because if we keep going, it's just gonna get bigger, right? The node, yeah, we take this node and then we take this node, right? So this is the merge. What are the other situations? Well, the other situation is it never say it's connected. Yeah, they never say it's connected. So yeah, either they're connected or they're not, right? So if they're connected, they're either on a path or they're not on a path. So that's the two scenarios. So the other one is they're not connected. If they're not connected, then cannot be reached by both. So yeah, no, it's not gonna work. So I have three scenarios. So what I think is I will go just traversing from one node. Doesn't really matter. We're traversing from node one, and then we produce a array, right? Visited, and then if it's visited, we'll just check. Okay, and if along the way I hit, then yeah, voila, lucky you. If not, that's fine. So we get this, and then we traverse from the other one, right? And then we use the same visited. So if we traverse the other one, and we find a node that has been visited before, that means both visited. So that is the node, right? That is the node. Or if I hit the other one, yeah, it's the same. Like we'll mark itself as well. We mark itself, and then the first one I make is the one. Or if I don't hit, I guess if I go through, I didn't hit anything, then that means it's not. Okay, that seems to be reasonable. I spent a lot of time today. I waste a lot of time today trying to do some over engineering with the help of Gemini. And in the end, I didn't really use the solution, but the experience was quite nice. It was a very interesting problem. I was trying to see, I'm defining a static function in C++ class. And since it's static, it cannot be defined in a pure class, in a pure abstract class, which means I don't have a contract to enforce any of the derived class to implement this static function. But this static function is quite important, so I want to find a way to enforce this contract. So I asked Gemini, how do I enforce this contract? And then Gemini was able to come up with a solution, which is called a templated wrapper class. And then we use that wrapper class to do a static assert on the existence of the static function at compile time. So I was very excited. Wow, I'm able to write some check at compile time that can enforce the contract that a class must define a certain static function. However, so that was all the excitement, right? However, as I was trying to, start implementing it, not copy and paste, but actually implementing it, the problem. Like you can see the problem because this check requires you to call the validate function. You have to call this check inside the code, right? You have to call it, and then during compile time, the compiler will discover the problem. But if you call this function, like if you have the um, mindset to call this function, that means you already know that this static function must be defined. And if you are calling it, why not just defining it, right? So it's kind of it doesn't make much sense to do this wrapper templated wrapper class, despite it being very cool. I have to say it's very cool, but overall it's quite interesting experience. um, I think I mean my opinion of these code LLM just to help your code, my opinion has always been very positive. Actually, I shouldn't say always. It's just since I started using it, it has been very, very positive. Simply because it saves me time, right? Saves a lot of time. I don't have to copy and paste. I mean, it's like a smarter way of copy and paste, and that's only just one part of it. Right? It is also the other part is this type of discussion. Like I was able to discuss this problem with LLM as if it's a real person. I mean, it's really bizarre experience, but it was good. Like it helps. I mean, but uh, what I can say is so far it feels like they always lean on the side of over engineering, because today later on I also had another problem about wait,
Está agradecido por tus...
está about how to, like, I have a class which has an overloaded constructor, and I want to build a factory pattern where I want to register this function, like save it in like save this function, this overloaded function's pointer in a vector. And to do that, I need to define the function um, type, right? It's a function pointer type, and I define it. But the function that's overloaded has like 3 different definitions. So I pick the one I need to use, and I define the vector using that. So far, so good. But then when I need to push it in, I want to push this function in, the compiler complains, which is very reasonable because I am pushing a function into this array which has one definition of the function. But the function is overloaded, so itself has 3. So when I'm pushing it in, the compiler doesn't know which of the overload I intend to insert. Like the compiler doesn't know, so it throws an error. So I passed this to Gemini and then was looking for something simple to resolve it. I don't know what. So Gemini first came up with a lambda function. I mean, which I understand. I mean, this is very easy to understand how they can work. Because the lambda function, you can define this the signature yourself, right? Arbitrary. So I can define the lambda function according to how the vectors element is defined. And then within the lambda function, I can call my overloader function with the exact argument that I need. So that's a very straightforward solution. But when I look at it, it has, very long, um, it just a little bit boilerplate code there. And yeah, I don't know if I like it. So I asked if there is another way to solve this with a simpler syntax. And then this is where Gemini starts to over engineer the heck of it. It suggested something called a bind front. I mean, like, I never heard of it before, right? And then it it doesn't look nice, and I say, yeah, I feel like maybe we can overload. Can we overload uh, the vector, or can we do some casting? So Gemini did some casting, some static cast, some reinterpret cast, and trying to cast the overloader function into the definition that we need for the vector. But again, like Gemini thought it works, but when you put it in the compiler complains. Right? It just kept complaining, and that was, I think, like a good an hour. I think I was just working on that one issue, and still wasn't able to solve it. So eventually, I went back to the beginning. Right, I went back to the beginning and decided, yeah, it has to be lambda. Lambda just so much flexible, so much more flexible to deal with stuff like this. So yeah, eventually ended with lambda, which is the first option that Gemini gave me, right? But then I didn't take it, so I spent like an hour arguing back and forth and trying to figure out what else to use. I mean, all of these examples just kind of, I mean, aside from obvious efficiency boost, but like this is definitely not an efficiency boost, right? Because I spent time interacting with it, and it also didn't give me the best answer initially. So spend a lot of time, but don't think of this as efficiency. Think of this as a learning opportunity, especially for somebody like me, who's still very very inexperienced with C++. So every time I interact with Gemini, I just see new concepts popping up left and right. And it's great because I can keep asking a question, follow-up question to help me understand a concept. And like today, like the wrapper, the template wrapper class, in order to do compile time check on the existence of a static function. This is like just blow my mind. I never thought like anything like this would be possible, right? And also the cast, all the things related to casting, function pointer, like I completely forgot that a function definition, like the name itself, it's a pointer, right? It's a pointer to a function. Like I've completely forgot about that, and all of these interactions just rehash the old concepts, relearn the stuff. It's really helpful. I feel I think like large language model, like one of the areas that shines the most is indeed coding, because the structure of the code has structure, has very well defined structure, so it's easy for the LLM to pick up patterns compared to if you ask it to like solve a logical problem, a novel logical problem. I don't see how it can do. Like you have something that's already there, like a documentation or some source code, and you put LLM on it, and it serves as a chatbot, right? It has great context. I think this is a great use case. Anyway, just a little bit insights of what I did today. Spent a lot of time, but didn't really have any fruition. But it's fine. Yeah, it's fine. All right, let's see. The constraint that each node has no more than one outgoing edges implies that there is no cycle. Yeah, there's no cycle. Thus, the wording of max distance is meaningless. Right? The max distance between two nodes is exactly the distance, the same distance between them. All right. So we will use probably DFS on any node to find what other nodes it can reach, regardless of distance, right? Regardless of distance. Then from the other node, right, we traverse again. we DFS again, but this time we keep an eye out for the nodes already visited in the first run. Right. If a node from the first, then the first node, and the first node from the previous exploration is encountered in the second exploration is the answer. Or if the two nodes do not share any other nodes in their path, right? We shall return what? We shall return -1. All right, I'm starting to feel the sleep is starting to creeping on me, so I need to do this as fast as I can. So what I need a DFS, but it can be void because I don't really need it, right? Void DFS. What do we need? We need a node. We need edges. We also need visited. Alright, visited. And then when you start, I say visited node or equal to true. Alright, I don't think it's an int. Alright, and then I go to all its neighbors. And the first time that I encounter something, yeah, okay, so let's just do int. For only one. And child shall equal to edges node. If node is smaller than 0, return. -1. Okay. And if visited child, I'll return true. I'll return child, first one that's encountered. If not, then we'll just return DFS child edges visited. Okay. And the first one we encounter, that's the one. Let's see, we do need Did it give me n? It doesn't even give me n. Oh, but edges size n. Edges is size n. Alright, so I have edges. I need to boolean. Alright, so when I say traverse, and how do I signal if it's found? Other node. Say if node is equal to other node, shall return other node. Edges node. Okay, I don't need this. Oh, okay. I do think just to keep it and make things easier. Too few arguments because I also need other nodes, and other nodes doesn't change. Okay, so we traverse from this and R1. Okay, from node 1, other node is node 2, and then we have edges, we have visited. Perfect. So that's int, and that's perfectly fine. It didn't find anything the first traversal, which is okay. Right, it's okay. Otherwise you go, so it will be -1, yeah. So we say if R1 is large equal to 0, I return R1. Otherwise we say, well, traverse from node 2. Right? The second round, we will just swap them around. Alright, we start from node 2, we have the edges, and then we have visited, and this one, if we can find, then that's the answer. Okay. Looks like ON to me. Oh. Ooh. The hell? I see. If child is large equal to 0. Now that I do this with child -1, and then we'll handle this. Yeah, it should be fine. Alright. Let's see. Nope. output 2, expected 1. Oh, I see. Oh shoot. We need to wait until the... Wait, really? No, that is the... Oh, it's the smallest index, right? It's not the earliest. Ah, okay. Yeah, I was wrong. Okay, yeah, that's fine. Just need the smallest index. Smallest index. Oh, smallest index. You have to keep traversal. Alright, so the DFS will produce that. And the second one around. If it's visited, what I want to know is what is the smallest on its path. What's the smallest node in the path starting from certain position? Okay. So we'll always return the smallest. Oh, we can fill. We can fill at the smallest. So it could be itself, and then we'll traverse, and then it will give me the smallest, so I can update this, right? And then when I DFS again, then the first time we hit will always give us, okay, yeah, well, change. So DFS smallest, DFS smallest node in path. So it's not visited. It's also not other nodes because that's not likely to be accurate. What we want is this. We can say the smallest node. Okay. So no smaller than 0, that's fine. And we don't have this. And we'll start always with smallest node. Yeah, this should be int max. Right, smallest node is node itself, and then we will check its children. Right, we'll check its children, so I can actually say this shall equal to minimum of this node and DFS visit edges node edges smallest node. Don't need this, don't need this, don't need this. And I will return smallest node and node. Node edges. Oh. Okay, so that's the smallest node, and almost exactly the same. Edges. Alright, so the node we traverse, we hit, first time we hit, we already got a minimum. Right, we already got a minimum. So if we get a, let's say if node is smaller than 0, return int max. Oh. And if it's already been visited before, right, if smallest node is larger or equal to 0, return smallest node. Right? Otherwise, it has not been visited before, then we just do the same thing, node. Huh? Smallest node. Yeah, we traverse once. We actually don't even need this. Right, we'll traverse it once, and then we'll traverse it the second time, which we can just return directly. No, we can say res equal to traverse the second time. Because it could be int max. Actually, no, I don't think it will be int max. It'll be some value. It's just in the DFS2, we don't get how can I call that? How do I know the smallest node has never been touched? Yeah, because the other body would just think of themselves, right? The smallest you can reach, the smallest you can reach. But we never really here is the failing. Like I feel the failing coming. So one already done, right? So the other one, it has to reach that, right? So we just go, 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 and then we reach, and that's it. If we don't reach, so I think we don't need a second. We don't need a second DFS. I think one is sufficient. We use one DFS to populate the smallest nodes, and then the second traversal is actually int node equal to node 2. Okay, and while smallest node, actually I need to take this -1. Ooh, int max. Okay, so while smallest node is equal to int max, right? It means it has not been visited before. Then we move on to the next one. So we say node equal to edges node. So while node is logical to 0, and so yeah, I just keep moving until a point it gets out. Right. When it gets out, basically we hit a node where the smallest node has a value. And we say we'll return. Right, we'll return this node. If it's equal to this, the first one is not the node, then we should do smallest node. Otherwise, I just keep going until the end, because I'm not setting anything. So it will just be smallest node is equal to this -1. Otherwise, smallest node. Should be node is smaller than 0. or yeah, let's be very explicit. Okay. Wow, it's taken an hour. Hmm? Oh, edges. No, I handled it. What? What was the problem? Okay, I don't know. I don't know what happened. I don't know when it's wrong. I guess we have to debug this. Oh man, God. I was trying to sleep earlier today, but this is not looking good from my plan. I have no idea. So something wrong here. So let's put it here. And let's just quickly let's go through this. I don't know what the hell happened. Okay. So we need to go edges node. Node, what's node? Node is 1. Should be 8. Okay. 8. 8 now is going into 2. Now go to 7. 7 go to 3. 3 go to 0. 0 go to 9. 9 go back to 2. Huh. So we start from 1, go to 2, and 2 go to something, and now go back to 2. Oh. That is a loop. That is a loop. So, okay, we need to have visited then. So the whole chain need to update. No, this is a. No, I think we can just traverse it in a loop. Go, 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 go. Right, we have the smallest node. But it has to be the smallest node along the way. So this one still is valid, but it's not valid. So, okay. So we go, 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 go. That if we hit something that cannot, that means, yeah, we have a loop. How you handle if it's a loop? Oh, if it's a loop, then everybody in the loop needs to handle. We can set smallest node first, right? And then we go to the next node. Try to find its smallest node, right? And eventually, if it leads to, if it's not, it will lead to a dead end. And once it's a dead end, then we'll get it is, and then we'll unwind it. Then we have everything. Now we have everything. Or if it hits something, right? If it hits something, then what we need to do is to get everybody to be the smallest. Get everybody to be the smallest. What do you mean to get everybody to be the smallest? Like starting from this, you can get the smallest within the cycle. How do we implement this? Maybe we just, find a cycle first. Because once we find a cycle, we cannot unwind. Because everybody in the cycle needs to be the same node. Because you start from here, you just go in cycles, so you find the smallest within the cycle. And then you get a one out, then it's the whatever's in the cycle, and then we'll compare to that, and compare to that, compare to that. So I think it's just okay. I think it all works so far, but I need to be a little bit more cautious. If smallest node, oh, hold on, let me finish it. If this is smaller, if this is smaller than int max, okay, so this is a cycle detected. We'll find the smallest, right? Within the cycle. Okay, so we start from a node, and then we go back to node, right? And then we say int min node equal to int max. Right, min node. Then we will go through int current equal to node. Well, min node is the current node, and there should be edges node. Well, current not equal to node. Min node is equal to minimum node current, no, min node and current equal to edges current. Right, so I move on to the next one, and then along the way I do main node, and once we get out, I have the main node, then I'll return. Then I'll say smallest node, I update myself, equal to main node, right? And then return main node. Right, and then if I return main node, and then they will all get a main node. Yeah, then the unwind will work. Otherwise, I say smallest node, we always do node itself. And then we'll say int main child, main node in main descendant. Right, I'll do a descendant. Okay. Right, so we basically pay attention that cycle is still possible, and it needs to be handled separately. Okay, so I'll traverse this and then traverse the second one and do the same thing. Okay, let's hope that it's right. I really cannot do another one, like do another round. Ugh. I said I cannot do another round, but I feel like I still have to do another round. Something's not right. 0, 9, 9, and remember to 2, 2 to 7, 7 to 0, 1, 2, 3, 4, 5, 6, 7, 7 to 3, 3 to 0, 1, 2, 3. Oh, 3 already go back to 0. That's that. Right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I have 0, we go to 9. Right? 9 go to 2. I was wrong. 9 go to 2. Position 2. So 0 go to this position 9, which is 2. 0 go to 9. 9 go to position 2. 0, 1, 2. 9 go to 7, right? 9 go to 7. No, 9 go to 2. Yeah, 0 goes to 9, 9 goes to 2. Zero and 2. 2 now go to 7. Alright, I'm 2, so I look, my next is 7, so then I'll go to 7. Alright. So next is 3. Yeah, 3 is, let's go back to 0. We're forming a loop already. What? This is bonkers. Yeah, I start from 1. No. Yeah, it's 1. And then next is 8. Oh, we start from 1. It's not 0. Okay. Yeah, I'll keep going. Okay, now notice 2. So start from 1, we go to 2. So 2, we already done, right? So from 2 go to 7, 7 to 3, so 2, 7, 3, 0, 2, 7, 3, 0, 9, 2. Oh, not everybody is the... Huh? Maximum in the path. No, it's you shouldn't wrap around, because if you wrap around, you say from this node, right, to that node, that's the path. Or you can say from this node to that node, because you're forming a cycle. So you say from node 2 to node 9, I go this way, so I traverse through everybody. So within a cycle, how to handle within a cycle? Yeah, I detect the cycle, and then because it says the longest distance, right? The longest, the maximum distance. So let's say between two, if I have 9, I want to reach 2, I can go that. The longest distance is minimized. What? Index of the node that can be reached from both node 1 and node 2, okay? Such that the maximum between them is minimized. The maximum between them is minimized. I feel my original one is correct. Return a node with the smallest index. I have no idea. I can't do this. I'll think about it tomorrow maybe. It's too late. It's way too late. I haven't even eaten yet.